Hello everyone, welcome to another section of the lecture series on measured theoretic probability. So today on lecture 3 we will be talking about existence and uniqueness. But before then, we left off some questions we needed answers for in our lecture 2. So the first question was, wanted to prove that f, which is the intersection of f theta, is a sigma field for each f theta being what? A sigma what? Field. So for f to be a sigma field, then the conditions for that class to be a sigma field needs to what? To be satisfied. So the first condition is that we need to have the whole space belonging to what? F. So since f is the intersection of f theta, for which each f theta is what? Is a sigma field, then we know that the omega belongs to what? To each what? F theta. Since f theta is a sigma field for each theta, then since omega belongs to each f theta, then if you intersect those f theta, you are still going to see omega belonging to what? To it. So this implies that the whole space belongs to what? The intersection, and hence the omega what? Belongs, or the whole space belongs to what? F. This condition is satisfied. And the condition 2 states that if you have A belonging to F, then its complement must also what? Belonging to, must also what? Belong to what? F. So we consider that A belongs to F, which is equal to what? The intersection of each of the F theta. This implies that A belongs to F theta for each what? Theta. This implies that the complement of A belongs to what? F theta. Since F theta is what? It's a sigma field. So F theta satisfies the conditions. So if you have A belonging to F theta for each theta, then you have A complement also what? Belonging to what? F theta for every theta. And if A complement belongs to F theta for each theta, then it belongs to its intersection, because you're going to see A complement everywhere in what? In F theta. So when you intersect it many times, you are going to see A complement there. Then it implies that the condition 2 is also what? Satisfied. So condition 3 star, for which we need the countable what? Union to belong to what? F. So we consider that if let A1, A2 up to infinity belong to F, then it implies that AN belongs to F theta for each n and what? And theta. So we know that F theta is a sigma field, and if we let AN to belong to F theta for each n, then it implies that the union of AN belongs to what? F theta. Note that F theta is a sigma field. So if you have all of these belonging to A, then it implies that the union, countable union, also belongs to this. And if the countable union belongs to each F theta, then it implies that the countable union belongs to each of what? Belongs to the intersection of what? Of each of what? F theta. And know that F is also equal to the intersection of what? F theta, hence proven. So this is solved. Question 2. Wanted to also know that F is a sigma field. If F is a sigma field, then what's the sigma field generated by what? F. Note the properties of a sigma field generated by a class. We need the class to be in what? In we need the class to be there. This implies that if the sigma field generated by F is equal to what? It's like the sigma field generated by F is the same as what? F, because F is what? It's a sigma field. So F will be what? In that class, and it satisfies all the conditions for a sigma field generated by a class, like for the sigma field generated by a class to be. So F is the sigma field generated by F is the same as F. Question 3. If you take A to be the whole space, then the sigma field generated by A is equal to what? The sigma field generated by what? The whole space. So we need A to belong to what? To that class. So we have A. So we have the whole space in here, and note that this is a sigma field, and it needs to satisfy the conditions for what? A sigma field. So if you have the whole space belonging to here, then its complement must also what? Must also be there. So we have the empty set also there, and the condition 2 is also what? Satisfied. And if we pick a countable, if you have A1, A2 belonging to this, to that class, then it implies that the union of it must also what? Belong to what? To that class. So we can pick A to be A1 to be this, A2 to be this, A3 to be this, A4 to be this, and so on and so forth. If you union them, you're going to see that the whole space also what? Belongs to this class, and hence the sigma field generated by this class is the empty set, and that of what? The whole space. Okay, so we move on to the next question that we're trying to actually solve. All right, so remember, under the axioms of probability, that is the condition 3, we needed the probability of the countable union to be equal to the sum of their individual probabilities. That's the countable additivity for each AK being what? Mutually disjoint. So we ask ourselves, does it imply that if we have a finite union, is it equal to the sum, the finite sum of their individual probabilities, since P was defined on a field, and for a field we just need what? A finite set. So we need A1, A2 up to AN. We don't need A1 up to what? Infinity. So since we define P on a field, why is it that we are including a countable operation in it? So we needed to actually answer this question. So the proof is that we let us consider A1, A2 up to infinity, which is mutually what? Disjoint. So this implies that if you consider A1, A2 up to AN, then we can also take AN plus 1, AN plus 2 to be what? To be what? The empty set. Then if you take the countable union of the AK, is equal to what? The finite union of what? Of the AK, since the empty set doesn't contribute anything. So then therefore, if you pick the probability of the finite union of the AK, it will be equal to what? The probability of the countable union. Note, we put this then what? Here, since you have this, we have it here, this is also here, so this is equal to this. And this, the probability of the countable union, is equal to what? The sum of their individual probability by condition 3 of what? Of P being what? Of P being a probability what? Measure. So you have the condition 3 being placed what? Here, which is also equal to the finite sum of their individual what? Probability, since the probability of the empty set is also what? Is 0. So then we have the probability of the countable union equal to what? The finite sum of their individual what? Probabilities. So this is also called the finite additivity property of what? Of P. So condition 3 implies what? This. If we take AN plus 1, AN plus 2 to be what? The empty set. So we have some properties of probabilities. We skip this part since it is actually basic. Example, if you have A, B belonging to F, and A is a subset of B, then probability of A is less or equal to probability of what? B. This is called the monotonicity property of what? Of P. We can show this. Also, probability of A complement is equal to 1 minus probability of A. This is the complement of what? The complement property of what? Of B, of P. For this one too, we can also what? Show that as well. All right, so we skip this part and move on. There are a lot of properties of probabilities you can actually think of. Now today, the interesting thing we want to talk about is that the fundamental question we want to ask ourselves is that, how do we define a probability on a sigma field? Note, a probability measure is defined on a field, not on a sigma field. Then how do we uniquely extend our P measure to what? To a sigma field. So always it is easier to start defining it on what? On a field. That's the small class. Then extend it to what? A sigma field generated by what? That class. So we sigmified it to include countable what? Unions. So we do this by the theorem. That's the Karateodoris extensions what? Theorem. So we state that a probability measure on a field has a unique extension to the generated what? Sigma what? Field. What do we mean by this? But we will prove the uniqueness part a bit in later lecture. And what we mean by this theorem is that if you have P, it's a probability measure on a field, as we always know, which is a subset of omega, and we signify that class and denote it by F, then there exists a probability measure Q on the sigma field generated by what? F theta, that's F, such that the Q measure, like Q, which is a probability measure for every A, is equal to the probability measure of A for every A belonging to what? To the field. Furthermore, if we take another probability measure, which is Q prime, it's another probability measure on F. It's like, furthermore, if we take Q prime, which is another probability measure on F, such that Q prime of A equal to probability of A for every A belonging to f theta, then it implies that Q prime of A is equal to Q prime of what? Q prime of A is equal to what? Q of what? Of A for every A belonging to what? F. So this is the uniqueness aspect we are talking about. So if this agrees with this on F theta, and it also agrees on Q prime on f theta, then Q prime of A is equal to what? Q of A for every A. So Q prime of A and Q also agree on what? On the sigma field generated by what? F theta, which is what? Which is our F. All right. So we are going to talk about this in our later lecture and see more example of it. All right. Thank you.